Hi again, everyone. Welcome back. I hope you've had a nice lunch. Uh, feel a bit rested before we come back to things this afternoon. I can see we're still missing a few people. I've also had a question just a few minutes ago, how to tell if a code is modern Fortran or old Fortran. It seems like things from old Fortran can still be used in a lot of modern Fortran. And yes, that's completely true. Completely true. Um, the simple answer is that you can't tell 100%. It's easy to mix a lot of old features and new features. Well, I would say old features, old style and new style code. It's possible to write, what shall I say, something something that looks like either but uses a lot of the syntax and features of the other. It's very interchangeable, and part of that is that there is really no strict versioning through the compiler of the standard. Most compilers will perfectly happily mix something that uses a little bit of Fortran 2008 or 2018 or 2023 even, and then also has some stuff which you only find in Fortran 77, like say data blocks or common blocks, which we won't even mention here because they're just not modern Fortran. Um, there are a few things that do sort of give things away. Um, Big things are things like capitalization in the code. Most people writing modern Fortran will just use lowercase. Smaller things like the two colons after you declare a variable didn't exist in Fortran 77 and earlier. Fortran 90 and newer, so modern Fortran put integer colon real colon to make it clear to people when you're looking at it that you're looking at a real or integer or whatever variable declaration. Um, um, the big thing really, something that maybe will give it away straight away, but it's still not completely certain, it would be if you're using fixed or free style uh, format. Um, if you're using fixed, that's the thing where you don't use the first 7 or 8 columns, except for very specific things like labels. And those files will have a name that ends in .f. If you have anything else, .f90, .f95, .f03, .f08, those are modern Fortran guaranteed. Anything using .f is yeah, that's a better thing to say. Anything using .f fixed style is guaranteed to be old Fortran. Anything using .f90 or modern will be working at least on a modern Fortran base. It could potentially be mixing in old Fortran code because it's perfectly allowed to do that. The compiler's backwards compatible. It's allowed to do so. But at least the way it appears should be modern. Whether the person who wrote the code is fully aware of everything is completely open to interpretation. Someone could write free format Fortran that looks completely like modern Fortran, but then declare their variables like they're working in Fortran 77. It can be messy, and it really kind of just comes down to what style the person who wrote the code was working towards, or what features were they using from modern Fortran. It could be that they have decided to write Fortran 77 in free format files. It isn't clear. What I'll say is that if you look at basically what we're doing in this course, the way that we're declaring things, the things that we're using like modules Things like this are giveaways for modern Fortran, because these things didn't exist in old Fortran. When we bring in user-defined types, those didn't exist in old style Fortran. So these are things which would only be used in modern, but there's nothing at the same time stopping people from mixing in old Fortran 77 if they want to. You just kind of have to hope that they don't. But that really comes, it comes into what you're working on. I mean, if anyone has any code that they'd like me to look at, it might be an opportunity to. If anyone wants to email me anything, I'll just put my email in the chat. Oh, and I see there's another message. So if anyone does want to just send me a message or ask anything more privately, I guess, about their code, please do just send me a message and I'll be happy to help if I can. So that's not really a very helpful, perhaps, answer, but it's so fluid, that the boundary between modern and old style Fortran, that there isn't a clean definition, other than what we're doing now is modern, and if it looks different, it's old style, is probably the cleanest way I can say it. And then we have another question: getting booted from ARCHER2 with the message network error, software connection. You might be able to. So what you want to do, Jordan, is you want to, and I don't know if it's possible in MobileX term, you want to tell it to send a keep alive signal. It means that there's something probably along the way between you and ARCHER2, perhaps something on your local network, or something in the country's network system between you and ARCHER2 that's going, nothing's happening, let's just shut it down. But you can hopefully tell it to use, okay, if you can, so I think you might be able to, if you go to settings, configuration, SSH keep alive, and you should be able to give it a value, which is the number of seconds for MobileX term to send the keep alive signal to ARCHER2 that says everything's okay, just keep things open. That would be what I would recommend trying. So yeah, if you keep alive, if you can find anything else related to keep alive, I'll just put it in the chat, because just in case anyone else is looking for the same thing. I know sometimes people do have issues with keeping their connection open. Yeah, so if anyone else is having issues, you can also set this in Linux-like systems on Mac OS. You can set it for SSH as an option. If anyone is having difficulties, do speak up and we'll work this out at some point. Okay, other than that, I will quickly, let me stop sharing the screen and bring up my code again. Where is my screen? There it is. So I put up a little hint before. Okay, it took a while to come up. Yeah, I put up a hint before lunch on what you might be wanting to do. You'd be declaring some reals. I should say this is all just working inside exercise 1.f90. Declare some reals, set the values of A, B, and C. We have some suggested values up above. And then I said in my little hint I put up before lunch, calculate D, the discriminant that determines what are the roots of the equation going to look like. Are we going to have reals or complex results? And then I had if ... question mark. So this is what you would actually want to do. Just say if D is greater than or equal to 0, then you know you're going to get real roots. If it's actually equal to 0, then your two roots are actually going to be the same, but we can calculate them the exact same way. And it's a little bit unpleasant to look at this code. There are not much nicer ways of doing this, but we haven't got to that yet in the course. So this is a slightly unpleasant way of doing it, but you say if our discriminant D is positive or equal to 0, then we've got real roots of our quadratic equation. So calculate that using just the standard equation, minus b, and then we use plus the square root of d divided by 2a, and then we calculate the second root by using a minus sign instead here, and then just print them out. If d is negative, then we know instead that we're going to get complex roots. So now we need to unfortunately calculate, because we're just using real variables here, both the real and imaginary part of each of those roots. And you can break that down like this. You say the real part is equal to minus b divided by 2a, and the imaginary part is the square root of minus d. This is okay because we know that d itself is negative, so this now is positive, divided by 2a. And then for the second root, we do the same thing, but we make the complex, so we make the imaginary part negative, and then print that out. And that works perfectly well if you've been doing something similar. If you do things in complex numbers, complex variables the whole way, rather than sort of hacking a bit some real variables to do the same thing, so just create ZD, Z1, Z2, then we can just create a complex version of the discriminant D, ZD equals complex D. And because that's now a complex variable, we can take the square root of it, and it will give us back a workable answer, a meaningful answer, even if it's got a negative real part. So that's fine, we can do that, and we can just calculate Z1 and Z2 in single lines of code and then print them out just like that. Much easier than doing all of this. So you can see it actually is really helpful having complex variables, having a complex type as a first class type to use in the language. And if I just quickly build that, exercise 1.f90, and then run it, it works like that. So here's the one I did calculating. So this is with the negative value of d, and it's worked. You can see the formatting is slightly different. I believe I'm using Cray at the moment. Yes. So this is some Cray Fortran formatting. So there's just missing spaces essentially. But that's worked very easily, very easily. One other thing, just very briefly to point out, I wanted a blank space in the middle. I wanted a carriage return. If you do print star without anything else, it gives you this blank here. It gives you a carriage return, just to make things a little easier, because all print statements and all writes in Fortran by default advance the line after it's finished printing out whatever you tell it to. So that print star says print nothing and advance to the next line. You can change the way that works with the write statements if you need to. Is that okay for everyone? Any questions about any of this code that I've just shown? Hopefully, with everything that we've covered this morning, this makes sense. This shouldn't look unfamiliar or confusing, I hope. But if it does, please do shout out. Okay, if everyone's happy with things, then I think then I'll quit this and we'll actually move on now. Where is my, here it is. Oh, and I should say, if you want to see the solution, there's a template available later on. I'm not sure why my cursor goes massive like that. It's strange, isn't it? You can look at later on. There's a template .f90 for a later exercise, and you can see it's slightly different, but it broadly shows the same thing. You can see what I've done in that. Okay, moving on then, past lunch onto loops as soon as the page loads. Bit strange. Why is it taking so long to load? There we go. Maybe the server was just feeling like it wanted to do its own thing for a moment. Okay, loops into loop control. So we're really building up the power of our code now. So in its simplest form, we do loops like this. We use the do word. We don't use for as such in Fortran. We do our loops with do, and it very simply starts with the word do and ends with ends do. Again, you might see older style code not using a space there, but modern style would say, yes, please put a space between end and do. And then whatever you do in the middle of the do and end do, you carry on looping through that forever. If you want to use a control variable, so this is much more like a for, say, in C or C++ now, then we'd at some point up above declare our control variable. We can say I equals 0. We'll work out how to actually integrate this into the loop itself in a moment, but you can do I equals I plus 1. And you can have some special statements in the middle of a loop that help you do things. So you might have some if statements that say when to exit the loop or when to skip loops. If you do this with the word cycle, it means skip this loop and move on to the next. So if you were coming through this loop and you worked out that yes, mod I2 is equal to 0, so is I an even number, yep, cycle means skip everything else and go back to the top of the loop again. Then you've got if I is greater than or equal to 10, exit. If you hit this exit, it means just skip out of the loop and carry on beneath. So now we have a loop here that doesn't carry on forever. We can skip certain iterations within the loop. We can exit the loop completely. You can do the same thing as before. Have a look stuff. I don't think we need to look at this too much. But we have the ability to name our loops, and again, to stop your lines running on all the way and getting this slightly unwieldy shape to them. You can use the line continuation ampersand to move on to another line to put your do's. So some outer loop ampersand do, some inner loop ampersand do. So we've named those two loops, some outer and some inner loop. And this is what actually is useful. You might have loop, loop, loop. You might have 7 nested loops or something. And if you have something trigger in an inner loop that means you need to jump out, you can end up having to write a lot of annoying code to bring you all the way back out again if you just have something like this, because this only brings you out of the loop that you're in at the moment. But if you say exit and then give a loop name, it now actually brings you all the way out of the loop whose name you give. You can also cycle in the same way, so you can cycle some outer loop, for example, in which case you'll just jump back up to the top of that loop. So this is actually pretty handy. It's still I'd say not exactly common to me to do this, but it does happen not uncommonly. And when it does, this is very, very handy. This can make your life a lot easier when that does happen. Maybe I'll just quickly look at example 2 F90. So let's go down to 04 example 2. You can see we've just got some loops, and we just say that we're just going to iterate I in the inner loop, but when we exit some outer loop, we would do this. So it would be that I is incremented in the inner loop, but because we exit the outer loop rather than some inner loop, we will never see never gets here printed. So if I just very quickly compile and run this, that will hopefully show what's going on. End of iteration. So it increments I and then ends, because it goes around and around and around on the inner loop, and then when we hit the exit condition, it doesn't just exit the inner loop, it exits the outer loop. And so we just carry on straight down, end of iteration, and the code finishes. So that's a fairly simple example, but yeah, you can imagine if you have loops inside loops inside loops inside loops, sometimes on occasion, this is very, very helpful indeed. This is the most common way though. I think most of the time we have some idea ahead of going into the loop how long we probably want it to be. And in those cases, we would use a proper controlled loop like so. So this is really like a for loop in C or C++ now. Do I equals 1 to 10 in steps of 2 is what this means. So we've already declared integer I. This isn't the same as C. It's probably obvious by now. C lets you create your variables wherever you happen to need them. So in C, you just say integer I equals 1 to 10 inside your for. Fortran says no, you have to already know at the top of your program unit what your variables are, what their names and types are. So we already know that there's an integer called I. All we're doing here is saying that I is going to go from 1 to 10 in steps of 2, and when it hits 10, we're going to exit the loop. And that just then looks like this. So our loop control says that our do variable, so in our integer I, for example, is going to start here and end here, and then optionally we can give it that stride. The way it actually works at the number of iterations, you can use this to work it out if you like. But that may mean, what you can see that there is a 0 here. That does mean that if you give it the correct mix of start, end, and stride, it may never go into the loop at all. If it's worked out that there's no point, it's not going to reach that upper value, then it will just not bother even starting the loop, and it will skip past it. The stride, yes, so the stride is, since it's optional, the default value is 1, makes sense. But if you do give it, it can't be 0. So let's just take a look at this quickly. How many iterations make a do loop? We've got example 3, which is going to contain 3 loops inside it, all using I, but we're going to go between 1 and 10 in different ways. So let's just see what happens. Let me move my screen around. This is what I'm used to. Okay, so example 3 looks like I just said, we've got those 3 loops. So let's try building it and then running it, and we get this. Oops. So the first loop, fairly simple, goes from 1 to 10 in a stride of 1, as we saw. So that just counts 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The second one, this one is more interesting. Second loop, 1 to 10 in the stride of 2. How does it get from 1 to 10 if it's going to move in steps of -2? The answer is it can't. It's going to end up doing this here, and it's going to work out that there are 0 iterations, and it won't even bother going into the loop. So if you can't if you can't reach the end that value from your start value given your stride, it simply won't do anything. The third loop, let's go from 10 to 1 in steps of -2. So it goes 10, 8, 6, 4, 2. That makes sense. The one thing you might ask would be, would it do iteration 0 and then realize it's overshot? The answer is no. It won't even overshoot. So it will move up to, but not beyond the end value. So it said that at the point it was 2, it would have overshot 1, so it just doesn't do any more. It leaves the loop and carries on. Okay, so I think we've covered everything there. Yep. So we've got a couple of exercises here. Do we want to do these? So these build on. I think it might be worthwhile doing this one. I think this one could be worth doing. So this goes back to so this is referring to an exercise from earlier today, which we didn't actually look at unless you were looking at it yourselves in any way. I think this is worth spending just a little bit of time on. So let's take a look at exercise 2. It's a little bit confusing, perhaps. There's a lot of maths going on, but you don't actually need to worry too much about that maths. I wonder actually if I might show something else. Oops, fine. Vim, exercise 2, please. Exercise 2.f90. So this is doing a real physical calculation. I think actually I'm just going to show the solution. I think actually to this rather than actually ask you to do it. I do think this gets a little bit confusing. So it's calculating this value C, which is a conductance value of flow in a narrow channel. And a lot of physical constants go into it. So we've got B, C, AK. This can look a little confusing. What really matters is that in here we've got a sum. And of course, the way to do a sum in code is to do a loop. You start off with some variable to hold the summed value, set it equal to 0, and then loop for however many terms you want to do it for. And then add it on as you go. And then by the time that you finish, you should hopefully have what is hopefully a decent approximation to this summation. This is meant to go on to infinity. Of course, we can't go to infinity. We'll have to go to some finite number of iterations. So where is the solution given? And I will just show that to you. Rather than actually ask you to work on it. The pi exercise is also interesting, but I think we might leave that for later on. I'll just quickly show it here. So the way we would do this then is we would have a real, and we're using our own type, KP, which we've made 64. So here we've said that real 64 is coming from use ISO Fortran env, and then we're using that everywhere. I'll actually show you something else that's I mentioned earlier in a second that can be helpful. Let's just call it sum. And let's just do, it's no longer the first term, so we'll do sum equals 0.d0. So I'm making that explicitly a double position. I could also do 0.0 kp would also be fine. And what I need to do is do I equals 1 to let's make it a parameter. Let's make a parameter integer, let's say, parameter, if I can spell, n iter, so the number of iterations. Let's make it 20. I don't know. 20 is a good number to start with. So I equals 1 to n iter, and that has an implicit 1. I won't bother typing it in. I'll do sum equals sum plus, and what we want to add on to it is everything in that tanh, everything here. So I will just copy this, and AK is calculated how? AK is equal to 2k minus 1 pi divided by 2. So we do something along these lines. We've just called it k equals 2k minus 1. So let's make sure it all works. Times pi divided by 2. We have pi defined, thankfully, up here. I hope I'm doing this correctly. Live coding, it's easy to miss things. Ends do. And then we can change all of this here for sum. I think. I hope I've done that correctly. If anyone spots that I've done anything stupid, please do tell me. It's a very good chance I might do, but I think that's okay. In which case, let's try and do that. Need to declare I. There we go. I've done something stupid. Thank you. Perfect. Integer I. Exactly. The compiler would have complained, but still, let's head that off first. Oops. ftn exercise 2 is what I actually want to do. Exercise 2.f90. K vim. Of course, this because I was just copying and pasting. So this isn't actually K, this should be I. It might have made more sense actually to use K. And I ran this course 2 weeks ago, and thankfully I remember that number is correct. Okay, so that's how that works. So hopefully everyone can see how this is working. We've just got our integer I, and then we loop through. We say I is going to go from 1 to some value n iter, which here we've just declared as a parameter. Let's actually just do this too. I just want to do this, 2kp. I want to make everything explicitly use kp as our kind. And we do the sum, and then finally we use the sum in that particular term of our conductance equation. Does that make sense to everyone? Any questions about that? Please shout out. Okay, great. I'm just going to very quickly show one other thing. I mentioned earlier we can use kind parameters to change the kinds of everything on the fly almost. So here we've done everything in real 64, which is great because we're doing a sum. And very often we want to do sums in as higher precision as we're able. Otherwise, we start to accumulate rounding error. We can actually change that just like that, real 64 to real 32. And because we've declared everything to be real kp, that instantly changes all of our variables to be 4-byte single precision floats. So we can very quickly recompile and rerun, and it's actually different enough, isn't it? It's immediately changing after just that, because that's already using all of our precision. Question, I'm a bit unsure about what kp is. You're just using it to set a kind. So I'll show you the code. So kp is just using real 32, and that just came from here. We just said only, so we can make it only real 32, oops, real 32, and real 64, let's say. So ISO Fortran env is giving us real 32 and real 64. These are only just integers under the hood, although we're never going to look at that. And then all we're doing is saying that kp, which is itself, yes, and an integer, is taking on the same value that real32 is using internally. And then we're using that kind parameter everywhere. So whatever the actual integer is, it could be 4, it probably is 4 with real32, and it's probably going to be 8 if it's real64, but it doesn't actually matter. It could be 12, it could be 1026, whatever. What matters is that internally the compiler interprets that integer when it's used here in a real kp to mean, aha, pi should be a real of whatever precision, whatever size in memory. It should be 32-bit, it should be 64-bit. It could be quad precision at 128. It could be half precision, maybe, at only 16, which is very inaccurate. But we choose kp here to be equal to real32, and then everywhere where we say, let's create a real kp, down below here, sum equals 0.0 kp, we're talking about variables and literals which are real32, because that's what we set kp equal to. If we want, we just change that again back to real64, and now everywhere where we're creating variables and constants and talking about literals with the kind kp, we're now talking about real64. So this is what I was saying. You can, that's perfect, brilliant. So yeah, you can very, very quickly, if you write your code this way, use this to check out how does my code change if I change the precision. Do my answers change? Do I get wildly different answers? Sometimes, you know, this can be the difference between a result being something that makes sense and it being infinity or 0 or nan or something. This can make a really big difference. It's sometimes very worthwhile just checking if the codes you're writing works if you change your kp between real32 and real64. Here, when we did it, we saw that our answer changed from 97,086, okay, 0.30227888, okay, 0.3125. That's actually fairly different, I would say. So this shows here that us using a double precision, real64 that is, to do our sum, actually, I would say was a pretty big help. This is much nicer answer than this. We've immediately started to go wrong just from the second decimal place here. Okay, I hope that's interesting. I hope that was useful. Again, this is floating point maths. Floating point maths is the bane of everyone's coding life, I think. It just makes things difficult and strange sometimes. And, oh, there's an expert question. What happens if you accumulate the sum reverse order in this case? Can you think why that happens? Let's very quickly, I want to actually try this out now. I'll try this in both of them. This is interesting. Let's go now from n iter to 1. So we're doing this in real64. I think I might use some new batteries in my mouse. Real64, let's compile again and rerun. What do we get now? This is interesting. Anyone have any idea what could have happened here? It's a little bit, it's a tiny little bit obscure. If anyone has any ideas, shout out. I'll let you think while I quickly do it again in real32. And let's see if anything changes here. I'll quickly rerun. If anyone has any ideas, please do type in chat. Well, it's broadly the same, though we've completely lost everything after the decimal place now. Okay, so what's happening is, remember that we have a limited amount of precision in both cases, whether we're using any floating point type at all. If it's a computer floating point number, it has finite precision. We can only go up to so many decimal places. Well, in terms of how the computer actually works, we can only go up to so many binary digital places, I guess, if you like, in terms of the binary storage of the mantissa. So we can only store so many places after the decimal point, equivalently. When we go from small to big, we start adding up small numbers plus a slightly bigger number, plus a slightly bigger number, plus a slightly bigger number, and then eventually we're adding a big number to a big number. That's what happens when we reach n-iter, if we were doing it the original way, like that. When we do it the other way, n-iter to 1, we're now, first of all, getting a equals a big number. Oops, this wasn't what I meant to do. And we add that onto sum. So sum is, after the very first term, a big number. Then we start adding slightly smaller numbers, and slightly smaller numbers, and slightly smaller numbers. And this doesn't work. We lose precision. And at some point, we can't add those smaller numbers. And things will start to round, and then they'll be rounded in a bad way. And we start adding things that are rounding up and things that are bigger than they should be, and everything goes wrong. We could go into this in detail and show. Let's maybe just quickly do that. Let's maybe just quickly do that. Print star a and this term here as we go. Okay, we'll do it the wrong way around first. Okay. Did I recompile it? Oh wait, am I talking about the wrong thing completely? n-iter to 1, n-iter 20 to 1. Is it not going at all? Let me take a look. And it's 20. Ah, of course. That would also help. Thank you. No, this is great. Live coding is a nightmare. And attach. Aha. Now we're getting this. Okay. And attach. Oh, so this is all going wrong. So this is actually helpful. This is actually helpful. So we're seeing things are going wrong completely. Yes. Oh, what was it? I must have been working something else recently that sets a step of -1 by default. I attach ABC divided by A. So we're actually just, oops, and if I go up here, down, that's real 32, 64. I do have a better example of this actually. I might dig that up. There's a thing called Gauss's sum, which is a really nice example. So it's actually not happening too much here. It's just that I was missing out the increment of -1, which was very silly of me. But no, I do have an example, something called Gauss's sum, which is just what you get if you sum all the numbers from 1 to n. And depending on how you do the loop there, you can get some horrifically different numbers. So if we made, okay, I think it might make a difference if we, let's think about this. This doesn't matter too much, so I'll only spend another minute on this. Let's make n-iter something really big, 10,000. And I won't print this out because then we'll not see anything. So I'll just comment this out. Okay. It's still actually doing decently. That's in real 64. If I go to 32, so if the stride wasn't negative, it wasn't actually doing the loop. I was actually skipping it entirely, so that was a complete bug. It's actually doing a decent job here. It's actually doing decently. It's doing better than I thought it would be. It's going still in the other way. I won't be joining. That's cool. So, okay, I might, if anyone's interested in this floating point weirdness, I think we'll move on from this for now for the sake of time. But if anyone's interested, I do have another code I can dig up. It's not part of the course, but I can add it to it if people are interested, just show it, that shows how doing these sums can really be affected by depending on which order you do the loops in, and also depending on what type you're using. But as you add these sums bigger and bigger and bigger, you have to ask yourself, is the precision of the sum at the moment, so is the precision that I'm using for sum itself enough that if I add this to it, is this actually going to make a difference to it? If I can only get down to, say, 10 to the minus 15 on this, and tanh ABC divided by a to the 5 is 10 to the minus 20, then this isn't going to actually add onto it. It will disappear into nothing. So depending on the way that you do your loops, the order that you do them, it can actually give you incorrect results. But sometimes something that you have to think about. Again, floating point numbers are interesting, and they're fun, sometimes fun in a slightly confusing way. But I think at that point we'll move on because we've already spent a little bit of time. Are there any questions about anything that I've just shown or loops just now before we move on? Anything in the chat from anyone? I don't think so. Okay, great. In that case, let's move on. And now we're really starting things arrays now. So we'll be, I think we've got 2 sections on arrays now, and then we'll have a little section on exercises to finish the day off. So arrays, of course, are very, very important in any form of computing, but here we're talking about scientific, mathematical computing. So of course we've got things like matrices and perhaps tensors that we want to think about, and of course this will be how we do those. So the very simplest way to create an array looks something like this. Inside our program, we'd have a declaration that looks like this. We just add this comma dimension 3 in this case, because we want A to be an array of reals of size 3. And this means that we're going to have A with elements A1, A2, A3. You can see we access these with curly brackets, with parentheses, sorry, not curly, round brackets. So A open brackets 1, close bracket, means we talk about the first element of A. If we just declare it like this, then we get a default lower bound of 1 and upper bound of 3. So there are some bits of terminology to remember here. The size of the array is 3, its lower bound is 1, upper bound is 3. You might also see again we're talking about, and it comes up so often, I do apologize, older style Fortran, where you might see something like this instead. Real : A open bracket 3 close bracket. This means the same thing, and You aren't actually disallowed from doing this. This is still valid in modern Fortran, um, but I think the way that we would advise people to write code is to do this instead. It makes it clearer that A has a size to it, has a is an array, in this case of dimension 3. It just hides it away a tiny little bit here. So this is slightly older. It's not wrong, but we'd maybe just recommend this instead. Something that is very important to note here is that Fortran arrays by default begin indexing at 1. Most other languages, I think it's fair to say, begin at 0 nowadays. If anyone's using C, C++, Python, all the usuals, they all begin at 0. And both ways make sense. There isn't really a right way or a wrong way here. It's only that it can make it difficult if you're switching quickly between the two styles. Beginning at 0 makes sense, particularly for C when you're talking about things like systems programming, because then your index is an offset in memory, and that makes complete sense when you're thinking about arrays in a C-like way. But Fortran is talking about arrays in a maths-like way, and arrays, if you think about just indexing a matrix or something, of course, they start at 1 and go on to n. So Fortran has its own heritage right back to the middle of the 1950s, and it said we're doing things the maths way. So that's why we see that difference. It isn't difficult to make the change. It's just something to make sure you do always remember. I do think Fortran makes using arrays very, very easy. It doesn't give you access to the memory in the same way, say, that C does. So that's why you wouldn't ever use Fortran for systems coding or the like. But for the purposes that Fortran is intended for, which is maths, science, and so on, it's really, really helpful. And we can start to see this here, because you can change those bounds. So we did mention up above, those are the default bounds, but they are only the defaults. Fortran arrays aren't just chunks of memory to do things with. They come with their own packets of information. They are in a way objects. So part of the information that they come with is what are their bounds. So here what we've done is we've said B is an array, and its lower bound is not the default of 1, it's now -2. Its upper bound is going to be 1. So now we have elements B -2, -1, 0, and 1. Sometimes that's very, very helpful. This can really make things like setting up our loops and working through big arrays very, very easy. When we do this, of course, we've got 4 elements, so a size is 4. You can also construct elements at the point of declaration, like this. There's 2 ways of doing it. These are both modern. I think the second way, this is Fortran 2008. This is much nicer. When I started doing this top one, this is Fortran 2003. You can see open bracket slash, and then you finish it bracket slash close bracket. I've found myself getting very weirded out by this for some reason. I don't think I liked this at all. I think there is a sort of similarity to something called common blocks and data blocks, which are from very old Fortran. And then I think the people who do the standard realized that they didn't actually need to do that, and that it would be much cleaner to do something like this. And square brackets aren't really used much in Fortran for other things. They realized that square brackets were available to them, so let's just do it this way. And I think this is much nicer. So you can just put square brackets and then put in the values to your array. want to take those to higher dimensions, and in that case, inside your dimension keyword, your dimension attribute, you put 2, 3, for example, here for a 2-dimensional array. So we say that that's rank 2. Again, this is our special array terminology. And then you can say what is its extent in each of those dimensions. So it has extent 2 in the first dimension, and extent 3 in the second dimension. And with that, it has a shape of 2, 3. And its size, then, you multiply them together for 6 elements. There's again something to remember which is different between Fortran and C here, which is the way that arrays are ordered in memory. So there are things to talk about here. Some of you might be familiar with things with the terms row major and column major, and we can use those, but it actually that can be, I think, at times a bit misleading, because there's nothing to say that we have to draw our array down on paper in any given way. And sometimes if we start thinking about things like columns and rows here, although it can be helpful, it can also lock us a little bit into thinking of arrays in a particular way, when sometimes it's more helpful to lay them out in our head or on paper in a different way. So actually, I think the way that's sometimes best to think about this is not to think about row major or column major order, but to think about which index changes fastest in memory. So in Fortran, we say the first index moves fastest. The opposite of that would be C, which moves the last index fastest and the first index slowest. So in memory, because remember, memory, as far as the addressing is concerned, is one-dimensional, means that the elements have to go one after another. So in Fortran, A11 goes first. First index fastest means that the next one is A21, then A12, A22, A13, A23. So 1, 2, 1, 2, 1, 2. The first index is changing from one to the next. The second index is only changing every 2 elements. So the first index is changing fastest. In C, it would be the other way around. We would go from A11 to A12 to A21 to A22 to A13, A23. Did I get that right at the end? I hope so. But hopefully you see what I mean. So the ordering in memory is different. And that does mean that if you're writing efficient code, you typically want to do it like this. So let's imagine that you've got a rank 2 array, A. Doesn't matter what its size is, but here we've said 20 and 10. Your loops should look something like this. You want to have your innermost loop be indexing over the variable that's the first element of your array. And then you move outwards. So you can imagine perhaps we would have even a rank 3 array. So ij, k, in which case the innermost loop would be I, second one would be j, and the outermost loop would be k. And that way you'd be making sure that when you're asking the CPU to roll through elements of an array and do something to them, it would be doing so in the most efficient order for getting and putting that memory from the main memory back into the registers of the CPU with a cache back and forth. This way should be fastest, should potentially give you some very big speed ups, depending on what you're doing. This can be something nice to do if you're just looking through completely unoptimized code to try and speed things up. Yes, so does that make sense to everyone? Sometimes talking about memory can be a little bit weird if it's something you're not used to, but does this make sense to everyone when I'm talking about the way that indexing works? Are there any questions? Okay, nothing's coming through, so I hope that's okay. If anyone does have anything, yeah, please just let me know. I'll be happy to help. Um, yeah, so everything here is going to be rank 2 arrays. I don't think in the course we ever go above rank 2 arrays in any of our examples, but there's nothing to say that you can't go on to at least rank 15. So that's what the standard requires. So compilers have to be able to allow rank 15 arrays, but there's nothing to say that a compiler can't go even further. A question: does rank 2 mean two-dimensional? Yes, yes, exactly. Rank 2 means two-dimensional. Rank 3 means three-dimensional, and so on. This is just array speak, I guess. Um, You don't understand. Okay, I don't understand the difference in syntax for bounds and dimension. Um, so there isn't really a difference, to be honest. So in its simplest thing like this, we say dimension 3. Here, all we're saying is I want an array of size 3. It's rank 1 because we've only given it a single value, 3, and we've said 3. So from that, the compiler says, okay, if all you've given me is the size, in that dimension at attribute, then that means I'll go with the default bounds. And the default lower bound is 1, and the default upper bound is whatever the size is. So from this, with the size of 3, it goes, okay, lower bound of 1, upper bound of 3. If you do it this way, it reads it slightly differently. So now we're not providing the size explicitly. Instead, we're now saying that the lower bound should be 2 and the upper bound should be 1. Maybe an easier way of thinking about it actually could be to instead, in this way, assume that there's an implicit 1 colon here. So dimension 1 colon 3. But because the 1 colon is the default, we don't have to bother providing it. If we want to do anything that isn't default, then we do. So now we say -2 colon 1 to say, actually, we aren't going to start at 1 and go up to whatever. Instead, we're actually going to start at -2 and go up to 1. Does that help at all, or is that still confusing? Why isn't dimension 2, 3 using 2 as a lower bound? Because here, this is a comma. So comma means that we're now separating the different dimensions. Yeah, so this means a ranked array. The first one is going to start at 1 and end at 2, and the second dimension is going to start at 1 and end at 3. Up above, this is a colon, so this means something different. So colons in Fortran are always talking about taking out slices or ranges of something that starts at one value and ends at another value. We saw something similar for strings. Remember, if you talk about string open bracket 2 colon 4, what we're asking for are the second, third, and fourth characters in the string. So it's always the same. Whenever we use a colon sandwiched between a pair of numbers, what we're talking about is some range of values starting at the left and going to the right-hand one inclusively. Okay, I think that helps. But no, this is good. If anything doesn't make sense, just shout. I mean, I understand this. My own brain begins to break down a bit when we talk about reshaping, and I always have to break out the pencil and paper to draw what I actually want when I do this. So, so if we wanted, we can now change the shape of arrays. So we can use the reshape in intrinsic function. And intrinsic takes two things. Here we've said first of all, is an input array. So this is an array. Remember, it's got the array constructor, the square bracket. So it's a one-dimensional array here. 1, 2, 3, 4, 5, 6. Okay, that's got size 6, but it's one-dimensional. But then we can say shape it instead as a rank 2 array of shape 2, 3. Integer dimension 2, 3. So we've taken here a one-dimensional array and reshaped it and then stored it in the rank 2 size shape 2, 3 array called M. And that's actually very helpful. There are some very clever uses for this when you're trying to work out how to step through things. Reshape can change your view, if you want to call it. I think that is the correct term, the view that you have on data, and really make things helpful sometimes. So it's worthwhile remembering. Fortran has a lot of support for arrays. It does a lot more with arrays in the very core of the language than most other languages do. A question is M 1, 2, 3, 4, 5, 6 or 1, 2, 3, 4, 5, 6? That's a very good question. Let's find out. Let's just do it in a bit of code. Let's see, 05 arrays. Let's just vim reshape.f90. So let's just write a little quick program to do this. Oops, I didn't give it a name. That's a terrible name to give it, but I can't think of anything else. Reshape prog. Oops. I need to change my vim settings to stop it indenting so much. Reshape prog and implicit none. And let's just copy and paste it. And then we can do, this will also show you how it prints arrays. If I just print star m and then just ftn reshape.f90. So you can see I haven't had to do anything to get access to those array intrinsics. It does this. Okay, now what does that actually mean? That's not very helpful. Let's try a module load again of GNU. That might do something else. I'm not sure if it will or not. It doesn't, no. I think again, I think the way that this is actually working. So I don't like going to it, but if it helps, the way that you can think of this is the number of rows and the number of columns. Again, that can restrict you into thinking about how to do this. But this is saying we've got 2 rows of 3. So if you like, it's actually going your second way, Victoria. So we could also try this. Let's try do integer. Let's make an I and a j. So we'll do some manual printing. This could help in a later exercise, actually. You may want to take note of this. So let's do j equals 1 to 3. And then inside that, do I equals 1 to 2. And then let's do print star. I'm going to show you something here. This could be helpful. There is something later on. So we'll do write star star. No, I can't do that, can I? How can I do this? Can you print a row or column of an array? Yes, you can. Do I want to? I don't think I do want to show you that now. Maybe I'll try this. I will actually show you this. So this is actually in the next lesson. So I'll just show you now. Let's do this. Yeah, this is not exactly. Let's do I equals 1 to 2 and do. But this doesn't actually. I'm trying to think of a nice way to show this. So the way that you do it is like this. So this is an array slicing operation. We'll be seeing these in not very long. So when you refer to an an array, you use open bracket, and then, oops, and then inside the brackets, you just give the indices, and here I'm talking about index I, and then colon for the second index. So this is the 3. This is going to show you this. If I compile this, 135246. So that's what's happening there. If I instead, because the first index is changing fastest, so actually it's more sensible to do, oops, no, this isn't right at all, to show this. Oops, no, it's not at all. 1 to 2. You see, this is why I do not like doing it this way. The easiest way with 2, 3, 2 rows of 3. Wouldn't it be 1, 3, 1, 3, 5, 2, 4, 6 if it goes through it as 1, 2, 2, 1, 2, 3, which is actually what we just saw. Oops. I'm still, what am I missing? And delete, replace with colon. This is actually what you had done. Yes, 1, 3, 5, 1, 3, 5, 2, 4, 6 is the correct reshape. I really find this very confusing. As I say, I have to break out the pencil and paper every single time, and I don't have any with me. 1, 2, 3, 4, 5, 6. So yes, it's going like that, and it's reshaping it that way. You can change the way that it reshapes as well. So there are other options that you can provide to this. So you can change the dimension that it's going along. So you can change it to get something more like what you have Victoria. So it's very flexible, and too much apparently for me to think about while also talking to everyone. But no, yeah, that's right. So it goes 1, 3, 5, 2, 4, 6. This is, there are other things we can do, particularly if you want to print them out, but it goes a little bit further onto what we'll be doing tomorrow. It requires some formatting stuff which we don't talk about until I think either late tomorrow morning or early tomorrow afternoon, perhaps. I can't quite remember. But I think for now the main thing to take away is that all of this array functionality is built right into the language, and I think the main thing actually that is useful here is this little bit here. Array slicing operations are very helpful in Fortran. They let you in some cases completely do away with loops. There are things that in C, for example, you'd need to do very big complex loops for, and in Fortran you can do them in a single line of code. I think it's probably more helpful if we were to move on towards that. I'll leave that there for now. Is that okay for everyone? It can be confusing. I find it confusing, to be honest. As I say, which indices go where when you reorder in which way. But is the general functionality here okay with everyone? The fact that doing this is possible, at least. Okay, I think it is. I think that's okay with everyone. Okay, so in that case, let's move on. Brilliant. Okay. Let's just take a quick look at example 1. Let's take a look at that. Example 1.f90. We've got some things in here. So we've got reshape, which I at least was just getting very confused by. Some array constructors. These are very helpful. We'll see more about these later tomorrow afternoon, I think. We can actually query at runtime the bounds of our arrays. As I say, arrays in Fortran are kind of like objects, and coming along with them are packaged information about what their bounds are. So we can actually say, is our bound -1 or -20 or 50,000 or whatever. And we can also query the shapes and sizes of our arrays. These are all things which we can grab at runtime. So let's just quickly take a look at that. You'll see that we can be very flexible very easily using arrays. Oh, this is a better way of printing it out. They've gone into the efforts here. So the bounds of A1, fairly simple, 1 to 3. B1, a bit more different. We can see here we were able to query what is the bounds, the lower bounds using the lbound function. Of B1, it was -2. So just the lbound here, lbound B1 gave us -2. When we ask it for the size of M, it gives us 6. When we ask it for the shape, that returns an array, and we've just printed out what that array is, 2, 3. Then finally, we've printed out the array in order, and that's been much more helpful. This is much more helpful. So here we have the ij and the value. 1, 1, 2, 1. So yes, that was exactly what you said, Donovan, wasn't it? 1, 1, 2, 1, 1, 2, 2, 3, 1, 3, 2, 3, and the values going up in order. So that hopefully makes a little more sense. I'd say if anyone's a little unsure about this, maybe come back to this little example that will hopefully get the right picture in your minds of what's going on here. If you're struggling to think about which things go in which order. Okay. So all those arrays that we've been talking about so far have been static. Often you can't do that. You need something to dynamically create at runtime. Maybe you are reading in some data from a file, and only in the file is it actually said how big your arrays need to be. Perhaps depending on the first line of the file, it's going to say 2. Maybe it's going to say 10,000, and that's the size of the data that you're about to read in. In that case, you can't say at the point in your code, you can't hard code in what the size should be. You have to leave it allocatable, as we say, for some point later on during runtime. And in that case, you add this extra attribute, allocatable. So as I said at the very beginning, Fortran likes to be verbose. It likes to spell things out pretty literally. So we're saying A is an allocatable array because we're going to allocate it and deallocate it as we like throughout the course of the code. So we start off by saying A is an allocatable array. You'll see that the dimension arguments look a little bit different here. We've just got colon, comma, colon. There aren't any numbers in here. That's because we can't say yet what those numbers are. So we're just putting in colons as placeholders. We're saying here it's rank 2 because we've got different dimensions separated by a comma. So a rank 1 allocatable array would just be a single colon. Rank 2 is what we have here, colon, comma, colon. Rank 3 would be colon, comma, colon, comma, colon, and so on. So we just defer the creation of each dimension by adding a new colon symbol to it. At that point, we know that A, so at this point in the code, A is a name that the compiler knows about, but it also knows that the array it's talking about doesn't actually exist yet. It's only when we reach this point here that we actually create the array in the memory. We allocate another intrinsic function, A, and this time we actually say what those limits should be. At that point, we can actually go ahead and start to use it. We can start using A just the same as we did the arrays up here. We can do whatever we want to with them. And then at the end of it, when we're done using it, we deallocate it. you don't technically have to deallocate things, because at the point that the program exits, all those allocatable arrays should be deallocated for you. But it's still considered good practice to sort of block off the region, I guess, where you know that it's containing data, where you know it's supposed to be usable. And also it can potentially prevent you from running out of memory during runtime. It's possible for you to create some really huge arrays here, which will use big chunks of memory. But if you keep on allocating more and more and more, at some points you could run out if they're big. So it's probably good to do that if you want to. The question: can you deallocate single variables as well? No. What you should be able to do, I think, I've never known of anyone doing it, but I think you should be able to, if you wanted, just to create an allocatable array of size 1 and use that. I think the reasons for doing that would be quite limited, at least as far as I'm imagining. Perhaps you have some use case I'm not aware of, but because the space to use it would be fairly small, unless it's an allocatable derived type, which is huge, I guess, could be something. But I think if you really wanted to, you should be able to just have an allocatable array of size 1 would do that for you. But no. So Fortran likes to keep concepts together. So allocatable has to be there. If you tried to allocate or deallocate something, an array that wasn't allocatable, you would get an error. Oh yes, and the bounds are worth mentioning. So this is just the same as before. If we don't mention anything at all here about the bounds by putting a colon in here to say this is the lower bound and this is the upper bound, then by default everything will just take on a lower bound of 1 in each dimension. You can go on with some extra optional arguments here. One is that you can provide a source argument to it, which lets you actually create the array and at the same time copy values into it. You can also use the source to say, to basically create a whole copy of an array. So if you have an array of this shape containing this data, you can do that. And we'll see a bit about that later on. And you can also get a stat value. So stat equals scalar int variable. This variable will come back to you. If it comes back to you with a 0, then that means that the allocation went through okay. If it comes back with another value, then that means something went wrong, and you probably need to, at that point, to look into the compiler documentation to find out what the number means. I'm imagining probably the scenario here is that you couldn't allocate the variable because you couldn't allocate the array because perhaps it was too big and you ran out of memory for it. So sometimes you might want to do that. I think this would probably particularly be useful if you were expecting the array to be huge. It might be helpful then to say, to handle the error a little bit more cleanly if it comes back with an unsuccessful allocation. Something that can be helpful if you've got a big program with a lot of flow of calls and logic is you might have a point where you're expecting to use an array, an allocatable array, but you aren't yet sure if it has been allocated. And then you can just use the allocated intrinsic, provide to it the name of your array, and that will come back as true or false, depending on its status. And then you can choose to do things or not. So something as well that's very common is for, at some point in the code, just have something like if allocated m, deallocate m. So you deallocate it, but only if it's already been allocated. Of course, you can't, if you were to try to allocate it and it had already been allocated, then you'd have a runtime error. Okay, do we want to do this? We've come past this computing pi a few times. It's already 10 past 3. I think it's probably better to skip this for now and perhaps go on, yeah, perhaps take literally a 5 or 10 minutes break and then come back to the last section for today. I think we'll do that. Maybe we'll take I think we might take a more close look at some of these, because this is actually a fairly big exercise. I think we'd need more than 5 minutes. I think we'll want to come back to it later on, perhaps tomorrow, and look at it in a bit more detail then. We should have more time then, I think, for this. Yeah, I think we'll do that. So I'll just very briefly mention, because arrays are fairly complex structures in Fortran, you can also ask for extra help from the compiler. So it's very easy in any language, it doesn't matter what you're writing, to be working with arrays and find that you're talking about an index which shouldn't be, which is out of bounds. But Fortran can actually help us along the way. The compiler can inject some code to the compiled application, so that at runtime, so this works for allocatable arrays as well as for statically allocated arrays. If you index an array out of bounds, it will tell you about it. And you just do that by adding an extra option to your compiler. So if you're using ARCHER2 and you're, well, any Cray system, and you are using the Cray compiler, you just add the -h bounds option. For the for G Fortran, you add -f check equals bounds, and you just put that onto your compiler like so, and then it should be able to tell you either at compile time or at runtime that you've been talking, you've been providing an out of bounds index to the array, and it will tell you generally what and where as well. That can be very, very helpful in debugging your code. It's certainly a lot easier, say, than if you're working in C or C++ and you're talking about an array. You go out of bounds. Often there's just no way to tell it's happened other than your result comes back wrong. So this can be very, very helpful. It's worthwhile checking with this option if you're running into some nasty errors, and it will hopefully come back and tell you if you've gone out of bounds. Okay, so with that, we're at 3:15. So I don't think we'll have any time for the big things today. Let's take a 10-minute break. So we'll come back at 25 past 3. So it's a slightly unusual time. And then we'll push through to 4 o'clock on, I think, this last bit of material here, probably. What are the exercises here? Okay, but yeah, we'll leave it there and come back at 25 past. So just a 10-minute break for everyone, just for a walk around and a cup of tea or whatever else you might need. So I will see you back in just over 10 minutes. Hi everyone, I'm back again. So let's push on with things once more. I think we are waiting for some people to come back. I think what I'm actually going to do, oops, that's the wrong thing. Let's share my screen again. I think what we'll actually do is we'll hold a poll just now, because I think we basically have a choice. Of what to do before 4 o'clock. Let's quickly do this, and I'll let people choose. Democratically, what are we going to do before 4 p.m.? So our choices are, this section we can compute arrays with pi. It just means taking a little bit of code to calculate the value of pi. At the moment it uses a loop, and instead taking that code and turning the quantities that we're calculating into arrays and storing those values. It shouldn't take too long, but it should show you a little bit about how to use them. It's not massively taxing. It might not take us very long at all. Only a few people have responded, so if anyone does have any preference here, please do say so. It's completely it's completely your choice what to do here, what you feel would be useful. The next section, that would be helpful to know, wouldn't it? The next section is on array expressions, so doing things using this colon syntax in the middle of arrays. That might help influence people's choice if they think, oh, I'd like to know about that. If we don't do it now, it'll be the first thing that we do tomorrow morning. So I think, okay, it looks to me like the balance is pretty clearly in favor of doing the exercise. We can maybe move on to, if it doesn't take long, we can maybe move on and do a little bit of array expressions and then leave the rest for tomorrow. But okay, we'll finish that. So let's take a little bit of time, maybe just 5 or 10 minutes, and do this. So there was a bit of code from an earlier exercise we didn't look at. I didn't feel it added too much on calculating pi using the Gauss-Legendre expansion. There's a template solution provided in the directory for this lesson, exercise1.f90, and so let's take a look here. If I open exercise1.f90, so the calculation is in a loop. It calculates 3 values, A, B, and T, where T itself uses P. All of these are subscripted n+1, so calculating a new value for each of these A, B's, and T's, depending on the previous value. So it is an iteration towards a solution. Start off with a bad number, and it gets closer and closer as we move on. And those values are themselves used to approximate pi at a given value of the iteration. So the question is, how do we calculate this now using arrays rather than anything else? So we've got this. So the question was, introduce array storage for A, B, and T, use a fixed number of terms, assign appropriate values in a first loop, in a second loop compute the approximation of pi at each iteration. So, I mean, let's just take a look at what's happening now. There's our loop. We calculate an equals a, so we do some initializations here for a, b, t, and p. An, we calculate first, also that's a new, if you like. But actually, it's more like a old, actually, isn't it? Yes, it's the previous iteration it's referring to. We update a, update b, update t using the old value of a, which is stored in an, and the new value of a, which is stored in a. Calculate p again, and move on. So p just doubles each time. So how would we do this? So let's think about how to turn these into arrays. The first thing we need to do is we need to decide, are we going to create these arrays with given sizes? So statically create them, if you like, on the stack, or are we going to dynamically create them on the heap, which means we can defer their size? Let's start off by just saying however big they're going to be at the beginning. So let's change this to instead go to, let's have an integer. We'll make it a parameter. And this is going to be the number of iterations. So let's just call it n iter. That's being actually controlled down below at the moment anyway. Let's just do it to 6. Let's just keep this the same. So let's do it this way. Let's say do, and we need another integer, which I'll add here, integer I equals start at 1 and go up to n iter. Everyone, I should say, please do work along on this at the same time. That's how you really get a feel for it, I guess. So we're going from I equals 1 to n iter, and then actually it makes more sense actually to just use n and not do anything else. Let's just do that. Let's just do it this way. And then everything is controlled automatically. So let's just make that n goes from 1 to n iter. So this, as it is, should work. It should, oh, we don't want to do this. We don't want to increment there. So let's start off n equals 0. Will it work? Will it work? Because I've just changed the way n starts off at 0. So let's make this start at 0, I guess. Okay, I think that will now work the same way, except I've called it I again, and it should be n. Okay, let's try that. Let's try building exercise 1.f90. Enter. Because I've got that back again. Okay, delete that. Hopefully that now works. Yes, that works. Brilliant. Okay, so you can see that as a iterating algorithm, it actually converges really quickly. I mean, after only after 2 iterations, it's already got how many significant figures is that? 8 or so. So it's converging very, very quickly. What we can now start to do is think about how do we change this now to use arrays. So our goal was to store A, B, and T in arrays. So let's turn all of these into arrays. That's very simple. We do dimension n iter after each one, like so. How we now do the initial values is another question. And actually, there's something else that we need to do, because we want them to start at 0 and go to n iter. So let's copy and paste this. So we're starting each of them at 0 and going to n iter. So that means that it actually has a size of n iter plus 1. That's something where the sizes are a little bit clearer, if you like, I think in C. And do the same here. P doesn't need to be an array. Now let's make sure down here that we store correctly the initial values. So A0, oops, that's not right at all. A0 needs to be 1.0 kp, okay? B0 needs to be 1.0 divided by the square root of 2 kp, because we're being very careful here with our kind parameters. T similarly 0 should be 0.25 kp. So there we've set the initial values. Just delete everything to the end of each line. So now we've just said here, A, B, and T are just arrays which go from 0 to n iter. Rank 1 At the moment, they're empty, but then down here we say these 0th elements of each are what we've given here. And now we just need to do a little changing of the logic here. And we do this like so. So now we actually need to change how this works a decent amount. We want to change each of these to now work based on the previous value. So we now want we want all of these to be working on, sorry, that's not right, AN. So the question was, how do we have a 0th element when this is a one indexing language? Because of what we did right here. Here we said by default, yes, the first element is 1. However, we've changed that. Here we've said now we're actually going from 0 to n iter. Remember, we can change the lower element to be whatever we want. If we needed it to be, we could have it start at minus 10,000. That doesn't make sense for us here. So let's change it to be 0 instead. However, if we hadn't done that, if we just had n iter, it would start at 1 and go to n iter. But we're changing that. We're saying start actually at 0, override the default, and start at 0 and go up to n iter. And that's just because that then lets us say what our starting point is. Sometimes you do want to do this. Sometimes it makes sense to start from 1. Sometimes it makes sense to start from 0. Because Fortran lets us change whatever those bounds are, we can just do that. So we've said, yep, the default is 1. In this case, it makes more sense to use 0. So let's start at 0. Okay, does that make sense? Is that an okay answer? I have another question. Is it not an plus 1 as a0 is defined? Yeah, it would be. But what I'm doing here, I'm changing this to 1. I'm saying we've already defined. Great, thank you, Victoria. So we've already done our 0th one here, if you like. So let's now do this. So now we're actually going to change the way that all of this works. And there's a big chance I'll make a mistake. So if anyone is doing this along with me at the same time and I make a very silly mistake, please point it out. So AN is referring to the old one. So here, this would now refer to AN minus 1. So our new AN is based on our old AN, plus it would be the old B as well, divided by 2. I think that's what the maths up here shows, is it? Yeah, so this is you can index it however you want. Are you talking about AN plus 1 or AN? We could maybe it would be better to do it that way actually. Maybe it would be better to start. You can do this however you want. Let's do it this way to stay in line. Let's do it this way to stay in line with the maths at the top. We're going to loop from 0 to n iter minus 1, calculating along the way AN plus 1. You can do it either way. It means the same thing. It just changes the way that you index things. So now we're calculating ahead rather than behind, if you like. Bn plus 1 is equal to the square root of AN, which is the old value there. So AN times B n still. Let's check that that's right. AN, BN, yep. And then T was defined all in terms of n's except for the final AN, which is the AN plus 1. That makes sense. So now we say Tn plus 1 is equal to T of n minus P and then we say this is just n, isn't it? And this is a n plus 1. So I think that's correct for the a's, the b's, and the t's. What else do we need? We don't need an anymore. We can delete that. How does p work? Let's just write this so far. P works by doubling itself each iteration. So that's simple enough. So P will just keep the same. Do we initialize P? Yes, we do. So we can just leave P, I think, as it is. Let's just try printing out what we're getting at the moment. We're calculating ahead. There are definitely better ways to do this. I'll check. Is everyone following so far with what I've done here? Thumbs up. Okay. Let's hope that's good for everyone. I'd say if anyone isn't doing this, I'd recommend maybe just having a wee go at it tonight or first thing tomorrow morning, just to make sure you can keep up with what's going on here. Okay, brilliant. Everyone seems happy with that. So so what index do we want of it here? Do we still want n here? I think that makes sense. Yes. So we are actually it could be better because we're doing a little bit of calculation here that we won't ever see the result for unless. Tell you what, I'm just being a little bit cheeky. Upper bound of ABT needs to be redefined, should be emitter minus 1. So you could do that. I'm being a little bit cheeky. You're right. So emitter minus 1 would make sense for the most part because we're calculating ahead. But this means we can do a final n plus 1 printout. It's not exactly clean code, but it will show us something. If we do here, we're sort of adding an extra implicit one onto the end, if you like. I think this should work just about. Yeah, it's a little weird. There are nicer ways to do this and less nice ways, but this will work given the code we had at the beginning. So I think that should give us an answer, hopefully, unless I've gone horribly wrong. Nope, still seems to work. Okay, so what we're doing now is we're just changing the way that it works. We're storing the values of A, B, and T as we go. Do we want to do that? For a little just test to show how we can do that here, how we can create these arrays with whatever bounds we need. You know, who knows what is appropriate, what is helpful for us, but we can set them to that. And to then show how we can loop through them. So we've got our loop control variable n, how we index them as we go. It should show you hopefully how this is working. What we can also do if we want, we can actually also store pi at the same time. So let's just, we don't need this anymore. So let's just change this to pi. And let's also turn P has the data initialized attribute. Therefore, oh, that's a very interesting error. Column 21. What column is 21? That's up here. Oh no, column 20. Line 48. What am I saying? Line 48. Line 48. Okay, that's unusual. maybe you need to copy and I think you might need to copy and paste your code in, Victoria, or if you'd like to email it to me, I can take a look, or we can just chat at the end of the course if that works for you. The TN+1 line. So data is an attribute you can give to things, but it's strange that it's being given here. I would say, Victoria, try to do module load progenv GNU. If you do that, I think I've already done it, haven't I? Possibly, I'm not sure. And then recompile the code, see if it gives you a different error, maybe something that's more useful. And if you do get another error, copy and paste it in the chat and we'll see if that maybe makes more sense. Otherwise, I think I'd need to take a look at your code more closely because it seems like something perhaps that shouldn't be there has made its way into it. In the meantime, yes, let's try and store pi as well. So let's make this also a dimension 0 to n iter. We're being a little bit crude in how we're doing it, but it'll work. So n, we'll just do it. Actually, let's do it this way. A whole new weird set of errors. Okay, something strange has happened. I would say either email your codes to me or hang about at the end at 4 o'clock and we'll take a look then. Don't worry, we'll work out what weirdness is happening in your code. Okay. And then I will just do here pi of n iter equals, again, all of this. Yes, and then let's just print it this way. Does this work still? Yes, thankfully. Okay, so that works. That hopefully gives everyone an idea then of how this works. Are there any questions about the code I've written? I know there are some issues with people here who found errors in their code, but has, at least looking at what I have done, does that make sense for everyone? Okay, I think everyone seems happy with that. So I think that was store any of the number of terms need taken to reach a converged answer. Oh, I don't think we have time for that quite now. So let's just say what would we do if we only wanted to store the number of terms taken to reach a converged answer? In that case, I would go back to the original code, which I unfortunately don't have anymore because I've just overwritten it while doing this. I'd have to clone the repository again. What I would do is I would store just the current value of pi and the previous value of pi. So for example, I would have whatever pi u equals ... Ah, thanks, Jordan. Okay, let's. Oh, perfect. That's perfect. Let's just do that then. Let's do that. Let's vim exercise 1.f90. Let's make it call it old or something. Let's copy and paste that in. That looks to me like most of the important stuff. Let's just call it program exercise 1. Yes. Okay, so if we just wanted to work out how many terms does it take, let's have 2 reals. Where am I going? Let's just say real kp, and we'll just call it pi and pi old for the sake of it. And let's initialize pi old to be something that we know is definitely not correct, minus 100, whatever. And here I would do the actual calculation for pi. Let's say pi. Okay. Then instead here, what I would do now is something just a little different. I would say if pi, let's do this. So this is often what you want to do when you want to check if two reals are changing. You can't do something like if real equals real, because they will never be the same. And generally, it's good enough to know that they're close within some tolerance. So let's say if absolute value of pi minus pi old is less than or equal to, say, some small, let's do 1.e minus 10. So we're going for a really high accuracy version of pi. Then I will print star converged at n, and then end if, and exit. So that's now my new exit condition. And here I will now also do pi old equals pi. So I'm constantly calculating a new value of pi, checking how different is it from the old value? Is it less than some number? And then exiting, and then storing the current value of pi into pi old, ready for the next one. And then here I would do print star pi equals pi. I think that should do it, I hope. I don't quite like having the pi calculation be here. I would have done this loop differently, but there we go. Let's see if this, it's not really a SS1 old anymore, if that works. If bracket ending. Oh, it seems to have liked it though. What's wrong in the if bracket ending? Abs pi minus pi old. I think that's okay. The compiler seem to like it. At least let's give it a go and see if it's. Oh, there we go. It works. Perfect. So that shows that we converge to within 10 decimal places within 4 iterations. In fact, we converge to more than 10 decimal places. So that's how I would do that. I mean, very often, I mean, I'm sure all of you have seen things like this before, is if the difference between two floats, because you can't do if real 1 equals real 2, because they will almost never be the same, except in very rare, strange circumstances. In this case, we actually have done. It's much more often to do if the absolute difference of real 1 and real 2 is less than some tolerance value, then take it as converged and exit. That's much more, this is the safe thing to do, I guess. Okay, is everyone happy with that too? So I've done very little here rather than just change the exit condition, store the value of pi, and then, you know, once it's converged, so converged at 4 iterations with that value of pi. I think everyone seems to have been following that along, so I hope that's okay. Okay, that seems good for everyone. In which case, given it's 5 minutes to 4, then I think we'll finish things up there. So, so tomorrow morning, then, we will get started with this section on array expressions and assignments, which goes a little more into the colon notation and how we can apply functions to arrays, some extra things we can do, like finding the minimum values, sums, so on. some slightly fancy stuff, wheres, still not super commonly used. And then I'm not sure, we might do the sieve of Veratasenes. That could be fun at some point. The main thing that we haven't really touched on today, if some of you may have noticed this, is there are, let me see, there are two mini exercises, it calls them. These were sort of meant to fill up the end of the day if there was time, and we just haven't had time. We've spent enough time talking about things that we haven't had any left over for this. That's not really a problem. These are two fairly big, fairly chunky sets of work to do. I think it's more likely that we might come onto the tri-diagonal system tomorrow. I think we don't really quite have a good enough handle yet on arrays anyway. So I think we'll come back to this maybe tomorrow afternoon. There's another one here which can be fun, working on the game of life. I think I'm more inclined to leave this perhaps until day 3 at the very end of the course. At that point, we'll have covered a lot of things, and all of them will be useful to do both of these. So don't think that you're missing out if you aren't doing them. We can come back to any of these challenges at the very end on Wednesday if necessary, and they'll still have something for you to do. They'll still be helpful and teach you something. So don't worry too much about that. Otherwise, tomorrow, what do we start with? So we'll be having array expressions. Yes, then we'll get onto more program structure things, modules and compilation of modules, functions and subroutines, array dummy arguments. This is section 14 is going to be a little bit confusing. I think this is a little bit weird, and definitely needs sketchbooks out to draw the arrays and work out what's happening. Then a little bit more about input and output in the afternoon. Depending on, I think I might ask you then how much of this is actually useful. Particularly section 20 name lists is obscure enough that it may not be of use to much people. I think I might skip over one or two of these perhaps, depending on how much use they actually are. This material, I should say, this website will stay here forever, or the closest approximation to forever. So whenever you do want to, if you want to come back and check out this material, it will always be there for you to come back and use it as a reference. So someone's using nameless at the minute. Okay, so that could actually be helpful to you. It may also be stuff that you already know, in which case it may not be, but it is there. Yeah, as we go on, all of this will stay here as a reference for you to come back to, in a year or two, 5 years more, who knows, whenever you might need it. So it's always there as a reference. And then at this point, this is us moving on to the final day. So yes, so I think we've got a lot of arrays and program structure tomorrow morning. In the afternoon, a little bit about input and output, and maybe we'll do that exercise here on tri-diagonal arrays, which really needs you to think about your linear algebra. I'm not sure how everyone here feels about linear algebra. If you're a linear algebra wizard, this could be really simple for you, but it's at least a nice exercise to do with arrays and loops. But otherwise, I think we'll finish there for the moment. So thanks for coming, everyone. I hope it's been a fun first day. If anyone wants to stick around with any questions about their exercises they've been doing, I'm happy to do the same and answer those questions or anything else. Otherwise, yeah, I'll let everyone go. Enjoy the afternoon and evening, and I'll see you tomorrow morning. Okay, that's great. Thanks everyone. I hope you have a nice evening. See you all tomorrow. Okay, thanks for the code, Victoria. I'll just copy and paste that now and see what comes up for me. I may as well share my screen again.
Yeah.
Where is my share? Entire screen. There we go. Let's find out what's going on. Something strange happening, isn't it? FTN X Victoria. There we go. Okay. Oh wow. Yes. I see what you mean. Oh, I've seen. I think I've copied your name at the top. Have I?
I'm muted, sorry.
No
Yeah, that
worries.
was the second lot of errors I got when I changed compilers, so
Yeah. So
it's
you
something
you
very like
you
that.
got the one error with Cray, and then Fortran gave you a whole pile of them.
No, I had multiple with both, but the more with Cray.
Okay.
No, more with more with Cray, and
Mhm.
because
Okay. So
yeah,
so they're doing okay, let's just take a look. I just want to see again what the Cray one does. So I think I can see um some things happening there from the errors that Fortran was giving. Let's just take a quick look at what Cray says. Cray um P has the date. That is a very strange error to give. I would not have expected to see that error. I have no idea. I think I'm going to go back to let's go back to plugin GNU. So I'm sure you know most people develop for the GCC compilers. They're the standard, if you like. It's what people assume their code will need to work with. So
mhm,
so I can see. So this is the first thing. It's often best to work at the top first, and then hope that if you fix, this first error, maybe it'll solve everything else further down. Um, okay, so let's take a look. So the first thing it's saying is that your yeah. So this is the first problem. N equals 0 to n iter, but here you're doing n equals n plus 1. That's what this first error is complaining.
mhm,
Variable n cannot be redefined inside loop beginning at 2. So when you start a loop like this and you use n here as you've done as a control variable, you're sort of handing control of this variable to the loop. Down
mhm.
here, you're then changing n again yourself, but you've handed over control to the loop. So that's two different things that you're trying to do. So
So
that's
I can
that's what the
get rid of
compiler's
that
saying there.
final line of the loop.
Yep. So you're saying here,
Okay.
don't do that. Instead, just trust that the loop here is going to do the right thing. So if we do that, it's one less at least. But this is very, very weird, isn't it? I do not. This is the thing. This is the same thing,
Yeah, I
but
don't understand. The problem seems to be with P, but I don't think I've defined
ah,
P any differently to how you've defined P.
I think you have actually. Or
Oh,
well, no, no. Actually, no. That's completely wrong. So you have defined P here the same way. That's
mhm,
correct. What's wrong with P is down here. Here, the code is saying P is either an array or a function. This is actually one of the things where Fortran falls apart a little bit, and I think that's why these
mhm,
error messages are really not very helpful at all. Actually, this isn't very helpful in
mhm,
the slightest, and that I think is actually an issue in Fortran, because in Fortran, um, array indexing and Fort and function calls look the exact same. If I had a function called p and I wanted to pass it a value of 1, I would do that. or just that,
So that's
because all
rather
you do is the
than
same.
only the first value of P.
Yeah, so the actual problem is that P is a scalar. It doesn't have dimension.
Okay.
If it had dimension enter, I won't bother putting it in, then it would be okay. Because what you're doing down here is both an array reference here and an array assignment here. But P isn't an array, it's just a scalar. So if you take that off there and put that off there, all we're doing is saying that P, and up here too, make sure that P isn't an array, then that should be okay. And yet, the reason for the very unhelpful error is because with the brackets on it, it looks like it's a function as well.
Okay.
So the compiler's basically getting very confused about what's an array, what's a function. The answer is it should actually just be a scalar. So if we try that now, that compiles, okay. And if then run it, it works.
Thank you.
So it was just a very small bug that the compiler completely failed to understand. Both compilers actually, I would have hoped that one of them would give a sensible error, but unfortunately in this case neither of them were able to be very helpful. But thankfully it was something very small like that. But otherwise that's working, so well done.
Thanks.
Okay, great. Well, I hope that's helpful. Any other questions just now, or okay to call it a day? And
I think call it a day. Yeah.
okay,
A lot
if there
to
is
take in.
anything, oh, I'm sure. Yeah, no. This used to be a two-day course, and I think that would have been a little bit unmanageable. I think it's a lot of information for 3 days, let alone 2 days. So yeah, if anything comes up, or if there's anything you'd like me to spend more time on or anything, just send me a message, however, and I'll try to do what I can.
Okay, thank you.
Okay, no problem. I hope you have a nice afternoon and evening, and I'll see you tomorrow morning.
Yeah, you too. Bye.
Okay, bye now.